Welcome back after the break. I'm Daniel Cunnama.
And I'm Jacinta Delhaze. You might recognise our voices from the Cosmic Savannah podcast,
where we give you up-to-date news and views about African astronomy. If you haven't heard the podcast, visit thecosmicsavannah.com. Otherwise, find us wherever you get your podcasts.
But back to the session now. We hope you enjoyed your break. This session will take an hour and 40 minutes and we will have 5 presentations.
As always, we'll be taking questions via the Slido Q&A app. Feel free to post your questions during the talk and we'll address them to the speaker afterwards. If you have any technical questions, please post them on the discussion forum.
Our first speaker is Amanda Weltman, who will talk to us about cosmology in South Africa. Welcome, Amanda. Amanda
Hi.
is the South African Research Chair in Physical Cosmology and the Director of the High Energy Physics, Cosmology and Astrophysics Theory Group at UCT. Over to you, Amanda.
Morning all. Thanks so much for the very welcome introduction and invitation to speak at this momentous occasion. I'm really delighted to have been included. So my thanks also go, of course, to the NRF who fund my research chair and all of my research. And my talk title is actually Cosmology with Fast Radio Bursts, which is some very exciting cosmology that we're doing right now in South Africa. So first of all, by way of introduction, what really is cosmology? So a lot of people ask, how do you separate between cosmology and astronomy? And I think it's worth thinking about some of the history of what cosmology has meant in the past and to different societies at different times. So the goals of cosmology is really about building a system of understanding, a way to understand and have beliefs about the origin and structure of the universe, and developing some kind of framework that includes humanity within the structure of what's happening on the very largest scale, so space, the planets, celestial phenomena. Historically, this has meant has often been underlain by deep religious beliefs and ideologies. And it's only really in sort of modern times that cosmology has taken the step from being a belief structure, a philosophy, a way of looking at the world, and it's become something very scientific by building our ideas with astronomy as a way of measuring and mathematics as a way of thinking of theories. And so we try to answer the larger scale questions in the universe using very often very small scale physics. And the point to sort of take away is the fact that sometimes our cosmology is still built on beliefs, and to really make progress, we may have to question some of our beliefs and put them on firmer footing with evidence. So advances in cosmology really require advances in astronomy, and that's why I think it's so important to have sort of these cosmology and astronomy discussions together. So what do we need to do to build a theory of the universe and understand everything on the largest scales? So we have 2 theory inputs. We need a theory of gravity. Our best bet is currently Einstein's general theory of relativity. And we need a theory of everything that's not gravity. So all of matter and the non-gravitational interactions. I have my son's t-shirt there from ICTP to sort of make it easier than typing out the full standard model equation. But that's really our best bet at the non-gravitational stuff to date. The other 2 things we need are actually not imposed by those 2 theories. They're choices that we make based on the data. So the data tells us that the best choice for geometry is that we do not seem to live in a special place in the universe, i.e. the universe on large scales is homogeneous and isotropic, and we still need to choose a topology. It has to match the data, but those theories don't force on us what sort of shape the universe is. Putting together these very, very simple theoretical ideas, we arrive at the sort of surprising result that the universe began in a hot, dense state that we now observe as the CMB. And this is sort of possibly the most famous simple image of cosmology. The original observation was COBE, the improvement is WMAP. I'll show you Planck a little bit later. But essentially, we observe a background radiation, a background temperature to the whole universe that's around 3 Kelvin, with fluctuations on the scale of 10 to the minus 5. That are these tiny little blips that you see on the image on the right-hand side better. So Planck has given us even better sort of precision. And as we've moved away from philosophy, we're moving towards a more precise way of understanding our universe. So in that gorgeous image on the top right-hand side, we're sitting in the bottom right-hand corner. and we're looking out at the sky, we see all of the stars, and as we see further back, we see the globe around us. We eventually see the CMB as this last surface of scattering very far away from us today. Now, we parameterize all the cosmological parameters in as few parameters as possible. We try to get them from fundamental theories, but it's very difficult to do so. So the list I've given you there is from 2011. And in principle, you would think that each set of data makes a more precise measurement. And that's just not turned out to be the case, right? We've hit against a stage we're at currently, where we have huge number of tensions in matching our theory to observations. So the two sort of most obvious and large ones, each one would take long talks and worth discussing, is dark energy and dark matter. So both of them, they take up large amounts of the energy density of the universe. Dark energy is around 68-70%, dark matter around 25%. Neither of them have been directly detected. We only know about them from indirect measurements. And neither of them have really strong theoretical foundations to explain why they should exist. They're just results that we get from the data, and we have to somehow understand. Likewise, it seems as though inflation is the most likely early universe candidate, but we don't have a theory for what the inflaton is, what is actually driving that inflation. We're missing all kinds of baryons, and I'll talk about those a bit later. We still don't fully understand galaxy formation, which was a shock to me when I discovered this. And the most recent sort of big tension, I think, in our cosmology understanding is the H0 tension. So the fact that we know the universe is expanding, we think we know the rate at which galaxies are moving away from each other, but the different measurements that we get from different scales in the universe and different time scales in the universe don't match. So if you look at the lower right-hand image, when I was sort of starting grad school, everyone had accepted that H0 was somewhere between 60 and 80. 70 was the sort of accepted measure. I know that when I was learning in undergrad, people talked between 50 and 100. Those results have got more and more precise. But the problem with the precision is that the error bars no longer include each other. And this lovely image on the left-hand side was made by Colin Hill only, 3 days ago. And you can see that the different measures, some of them have error bars that allow for the others, but some of them completely exclude each other. So something has definitely gone wrong. And Yinje Ma will talk more about this tomorrow, I believe. But this poses a question for how we can do better. So the one option is go back, look at the data again, look at the methods, the analysis, and perhaps someone's made an error. But there's so many results now that it would be unlikely to fit it all together in that way. It's possible that there's new physics. There are two sort of things we can do when our data doesn't match the theory. The one is to change the standard models, so look at new physics, and the other is to change the general theory of relativity, right? Those first 2 bullet points I gave you for a full theory. So the possibility is that there's new physics that explains why early universe measures and late universe measures, or small scale measures and large scale measures, don't match. The other option is that our theory of gravity is not right. And we often test our theories of gravity with cosmology, but we wouldn't be able to figure out what's gone wrong by doing that. So one option is to use gravitational waves as a testing ground for theories of gravity, and then put that back into cosmology. And my student, Irvin Martinez, is working very hard in this direction. Another option is to find completely complementary ways to those existing results to probe distance scales and cosmology to resolve these tensions. And this is work that I've been doing for the last few years with Tony Walters and Emma Platz, who are both part of my research group. And so there are examples on the slide of things you can do using cosmology as possible new measures. And this brings me to talking about fast radio bursts as a sort of, very exciting, relatively new result in astronomy that has immense potential for cosmology. So essentially, fast radio bursts are transients, something probably well known to the audience here. They were recently discovered, relatively speaking, only in 2007. And they went from being very few of them, few were found in archival data, some were found live, so to speak, to suddenly having several hundred. I think we're even pushing into the thousands very soon now, as more experiments looking for them have sort of switched on. The physics behind what drives them is not fully known, though we have strong hints. I'll talk more about that. And we don't know how many classes there are. It's not obvious that there should be only one. We just know that they're very bright and they're very brief. but the potential for discovery is huge with fast radio bursts. I've included just a few papers I've been involved in, and a very useful one is to take a look at our FRB theory catalog. This was really an exercise that my students and I launched into to try and understand what people knew about FRBs. And it turned out to be a very useful product for the community because there are so many theories. At the time, there were more theories than experiments, FRBs observed. And so you can see the wiki there and feel free to take part in it. So I've tried to collate everything we know so far. So we know they're millisecond duration pulses. We've seen them in the range of 300 megahertz to 8 gigahertz. Possibly they go even lower in frequency. We still have to look. Very few of them have been localized to hosts. Every localization is still a big deal because knowing the host allows you to understand the physics that drives them and allows you to do better cosmology with them. So localizing is a very important thing. Only a fraction of the parameter space has been observed, and we expect tens of thousands of them per day, just doing rough estimates of what we've seen so far in how many patches in the sky. Some of them are definitely known to repeat. Some seem to have periodic repetitions, but we're not certain. It's not clear if we're missing periodic repetitions in the ones that we see to repeat just because we only observe certain patches of time. They go out to cosmological redshifts and they're very bright. So that's great news for us because we can do cosmology with them since they're extragalactic. They're fantastic traces of their source environment. I'll explain why in a moment. And the key in trying to understand what we can learn from FRBs is separating out what effects come from the host, what effects come from the intergalactic medium, and what effects come from our galaxy. There are a lot of theories that can explain what drives them, and it's possible that there's more than one mechanism. So there are sort of fast radio burst stirrers as opposed to just fast radio bursts. We know that magnetars now are a very compelling source, as the soft gamma ray repeater within our own galaxy has been observed to have fast radio burst-like emissions very recently, including X-ray counterparts. So we know that counterparts are possible. So far, we've seen these. What other counterparts are out there? We don't know. And this is a really important project to look with different, both multi-wavelength and multi-messenger searches to find counterparts to FRBs. So the dispersion measure tells us really everything we need to know. The pulse arrives, and each part of the frequency components within the pulse are spread out by a 1/nu² behavior. And that's simply because the wave is traveling to us through a cold plasma, and the different frequency components interact with the matter along the way. And so we can learn a fortune just from that relationship. So we know that they are extragalactic because they're large dispersion measures. So a host that was within our own galaxy would have a much smaller dispersion measure. And they all appear to have host galaxies. So they exist where there already is matter, which is no surprise, but they're not necessarily associated directly to their hosts. So in terms of how to probe them with cosmology, we looked at, essentially everything comes from the fact that all your cosmological parameters are encoded within that dispersion measure. So I'm going to not dwell too much on this page, but it's worth sort of seeing that omega matter, dark energy, and curvature are all sitting within the right-hand side of that DM, and the baryon mass fraction, FIGM, is also there. So those are sort of very important things to realize, is that the cosmology is encoded within the dispersion measure. So you get 3 contributions, one from the host, one from the IGM, and one from the Milky Way. The Milky Way is well known. The host galaxy is the most unknown, and the cosmology is sitting in the IGM. So if we can get far enough out FRBs, we can reduce the effect of the host galaxy, but obviously that's a challenge in and of itself. So Tony Walters did this great simulation for us to see what we could do with a reasonable number. 1,000 felt like a lot at the time. Now it feels like very few. But FRBs up to a reasonable redshift of 3 with a Hyrax type of survey. And the truth is that you can't constrain cosmological parameters very well with only FRBs. If you add in other cosmology priors already, you can get slightly improved constraints. The most obvious one is on omega baryon, for the simple reason that they're probing the matter between us and the host, and so it's the baryons that they're probing. We initially wanted to constrain curvature, and you can only really get, with a non-flat lambda CDM model, you can only really get constraints on omega baryon allowing for varied curvature. But what we realized eventually is that we were going about this all wrong. The cosmology constraints that exist are far better than the assumptions that we put in. So we put in a fixed value for FIGM because we assumed this was a known thing in astronomy. And the more time we spent, the more we learned about how little we know. And we realized that actually FIGM is very unknown because of this missing baryon problem. So we know there are about 5% of the universe is baryons, but when we add them up, we only find 70% of the total. So 30% are missing and assumed to be sitting in the intergalactic medium somehow. And so that FIGM is the baryon mass fraction. It carries that information. And so we realized that you could get fantastic, you could solve the missing baryon problem if you get a fantastic measurement for FIGM and use the cosmology as the prior. And this paper was published last year, and very soon thereafter, I think people were working on this anyway, of course, but very soon thereafter, the actual observation happened. And this was published early this year with a lead author, J.P. McCart, in Nature. And you can see this absolutely spectacular result. Essentially, there's your burst happening outside from one galaxy. It's moving towards us in our Milky Way galaxy. And if I zoom in on that light signal, you can see the different frequency components. If they're traveling in vacuum, they all travel at the same speed. But if they hit a bunch of particles in between, this missing matter, the baryons, they are slowed down at differential rates based on the frequency components. And so essentially the purple light, so to speak, will reach us first, the higher frequency light reaches us first, and we get this spread in the result. And so this exceptional observation essentially solved the missing baryon problem. So there's really exciting foundational understanding stuff you can do with fast radio bursts, and there are a lot of papers in this area. I've just included a couple in the hopes of getting people intrigued in this area and hoping to start some more conversations. So there's very early universe physics that you can do, because if you can get fast radio bursts out to far enough redshift, you're able to probe helium reionization epoch, which would be very exciting. There's a whole lot of cosmology that you can do, the cosmology I talked about, but also if you can use fast radio bursts for the dispersion measure and associate them with gamma ray bursts for the redshift, you then it's the difficult part of the FRBs is not knowing the redshift. If you get the host galaxy, you've got it. But if you don't have host galaxies, the GRBs could do that for you. And so it's much easier to constrain your dark energy theory. And so there's a lot you can do. Each of these papers, though, has some assumptions, which is really important to realize. There's a whole lot of intermediate scale physics, so we could understand dark matter, possible dark matter candidates, machos, by looking at the lensing they cause for FRBs. So microlensing would give these tiny little doubled peak FRB signals. Strong gravitational lensing would give repeated FRBs with a time delay. And so understanding the substructure of FRBs gives us a chance to understand dark matter. And finally, there's all kind of fundamental physics you could do. If the photon had mass, you would also get this 1/frequency squared dependence, but you really need to know the redshift. So it's important to realize there's a whole lot of exciting things that can be done, but you need to know your priors. So where does this link to South Africa? Kavi will talk to you more tomorrow about the Hyrax experiment, but it's an extremely exciting experiment that we're in the process of building. It's a telescope array with, very similar design to CHIME, but instead of cylindrical telescopes, we have these parabolic dishes, which makes for a much easier calibration. And this is in the process of happening and being built. I just want to focus on the one aspect which is really important for fast radio bursts, and that's localizing them. So with the main array, we are able to localize a fast radio burst to around an arc minute. So in other words, we can say it's by this galaxy, which is nice. But if we can localize it to somewhere within the galaxy, there's a huge amount more that we can do. We can understand a whole lot of open questions about fast radio bursts, about the progenitor mechanisms, about being able to remove uncertainties due to the host, whether they're evenly spread across galaxies, which they don't appear to be. A whole lot of open questions can start to be probed by being able to get arc second or sub-arc second resolution, which Hyrax will be able to do because we have an outrigger program whereby we build sets of 8 little arrays very far away from the main dish. And so it's effectively as if we have a huge, one huge telescope, sort of the size of Africa almost, by having these the outriggers talk to the main array. So to sort of leave off, there's a huge amount that we can learn from fast radio bursts, not just scientifically, but also how we do science. So the fact that they were found originally with no technological innovation, just the fact that we thought to look in a different way at the existing data is something that I think is really worth taking away. We have a lot of data already, and just looking at it in a different way may give us huge new insights. Yes, we need new tech advances now to see new results, but we should never forget the existing data may have a lot of science hidden up in it. When we have limited resources and limited data, we introduce bias into what we follow up. So there's one very well understood FRB, and we keep studying it. And if we delude ourselves into thinking it's typical, then we will miss out on a lot of new information. So there's all kinds of important takeaway messages I think we can get from fast radio bursts. And just because we've convinced ourselves that magnetars are very likely progenitors, it doesn't rule out other mechanisms. I've always taken a Feynman approach to physics, which is that anything that can happen must happen. And so we have to rule things out. Either the data must rule it out, or there must be a theoretical explanation for why it cannot happen. And fast radio bursts give us a beautiful opportunity to rule out and constrain all kinds of other physics, and a chance for amazing collaboration. So it's been really important for me to learn about the value of astronomy and how important it is for cosmology and how they work together. And bringing the fields together and working across continents is really critical. And finally, just a big thank you to the organizers and the whole meeting for giving me, once again, a wonderful chance to take my head out of the everyday, ordinary problems of our Earth into the phenomenal, exciting space of the sky.
Thank you, Amanda. Thank you for an excellent talk. That was wonderful. Unfortunately, we probably have time for just one short question.
Yeah, we have one from the app. We have, would you rather have 1,000 localized FRBs at redshift 0.5 or 10 localized FRBs at redshift 5?
I'd grief. I think you could do a lot with either. I think if you had, I would rather have 10 at redshift 5 because that means that they exist at redshift 5.
That would definitely be exciting.
So that's yeah. I think we will definitely get the first eventually. The second, I'm not sure.
Thank you, Amanda. Thanks again for joining us.